All right, party people, let's talk about some water. What are you waiting for? Let's get to this. All right, so water is the most abundant compound found in living things. You are just made up mostly of water. You are a big fat bag of water. That's what you are. About 71% of the planet is covered in water. That doesn't mean that 71% of Earth's volume or Earth's mass is water. It's really just like a sheet of water on the outside. There is some down underground, but the vast majority of Earth volume-wise and mass-wise is not water. But the surface is covered in water. Water is H2O, which means that it has 2 hydrogen atoms and 1 oxygen atom. So it looks like this. If you take a look and you kind of look at it creatively, sometimes people call it the Mickey Mouse molecule because it looks like Mickey Mouse because it's got 2 little ears, 2 little hydrogen ears. A water molecule as a whole molecule has no charge. In other words, a water molecule is not an ion. However, water is a covalently bonded molecule because the oxygen needs 2 electrons and hydrogen wants to get rid of 1 in order for everybody to be happy and stable. Since that happens, we've got these polar covalent bonds. And the reason they're polar bonds is that oxygen has 8 protons. Hydrogen only has 1 proton. So if you've got an electron in the middle and you have 8 protons pulling this way and 1 proton pulling this way, 8 versus 1, the 8 is going to do a really good job of pulling on that proton. Or pulling on that electron, sorry. So oxygen has way more protons. So whatever electrons are being shared, oxygen is going to get it. Oxygen's going to win. And so most of the time, oxygen is going to get to hold on to those electrons. So the electrons are going to go oxygen, 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 and then every once in a while it's going to be like, whoop, hydrogen, oxygen, 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 oxygen. Once in a while it's going to go, whoop, hydrogen, oxygen, oxygen, oxygen. So those electrons are going to spend all their time there around the oxygen. What that means then is that you're going to end up with these little, this electron cloud, and the electron cloud most of the time is going to be around that oxygen molecule. So the oxygen is going to end up acting like it has a negative charge, and that's because it's got extra electrons. So remember that if we're talking about a neutral molecule, our protons and our electrons are balanced out. But if we now give oxygen extra electrons, then we've got protons and more electrons, so we're going to have a negative charge. The hydrogens, though, proton, electron, lost an electron, and so they're going to act like they have a positive charge. So the oxygen side of the molecule is going to act like it's negative, and the hydrogen side of the molecule is going to act like it's positive. So again, the oxygen is going to act like it's negative. This hydrogen is going to act like it's positive. This other hydrogen is going to act like it's positive. But the entire thing overall is neutral. So the charges are just within the atom, or within the molecule, sorry. Within the molecule, you've got these separate charges, so it's polar. But the whole thing overall, is neutral. So what will have happen is hydrogen bonds that form between water molecules, because the positive hydrogen atom of one water molecule is going to be attracted to the negative oxygen atom of another molecule. So again, we have negative and then our 2 positives, and here we have negative and our 2 positives. And so this negative is going to be attracted to this positive over here on this other molecule. So 2 separate water molecules actually end up attracted to each other. So how many hydrogen bonds can a single water molecule make? No, legit, I'm asking. What do you think? Come up with an answer. Okay, if this helps, here's a picture. Take a look. Now it's a little hard because this picture isn't 3-dimensional, so it's a little tricky and you can't really see all of them. But what you really get is one water molecule has the potential to make up to 4 hydrogen bonds. So you have that oxygen, you have the 2 hydrogens. This hydrogen can bond to another molecule, the oxygen. This hydrogen can bond to another molecule, the oxygen of another molecule. And then the oxygen part actually has 2 binding sites. So the oxygen can actually bond to 2 other water molecules. You can get 4 altogether. Hydrogen, hydrogen, and then 2 on the oxygen. So you can get 4 hydrogen bonds, so you can get this lattice work of water molecules attracted to each other. So just one more point for clarification. The bonds inside one water molecule are polar covalent bonds. So a water molecule is held together by polar covalent bonds. The bonds between multiple water molecules are hydrogen bonds. So polar covalent bonds are inside the molecule. Hydrogen bonds are between different molecules. Okay, so because of this, because of water's polarity, we have hydrogen bonding. And because of the hydrogen bonding, water is magical. Water is quite literally the reason there is life on Earth. If there were not water, probably none of the life processes that have made us or any other organism, that organism, would be able to happen. So water is essential, okay? So there are lots of really cool things that we get because of the polarity and the hydrogen bonding of water. One of them is cohesion. Cohesion is when water is attracted to water. And so it's going to give you this effect where you see things beating up. And that's because the water molecules are all holding on to each other and they're saying, hey, come be with us, come be with us. And so those water molecules are sticking together. So you see sometimes these really cool like drops of water where you're looking and you're saying, how could that possibly still be there? How has that not dripped off? Well, it's because water is holding on to other water. It's like if you could go inside to the water molecules, the tiny little Disney movie would be going on, going, hold on, don't let them fall, don't let them fall. And all the water molecules are holding on. They're saving each other and not letting them drop. That's what cohesion is. Adhesion is when water is attracted to molecules of other substances. So adhesion is the reason that we get the meniscus in a graduated cylinder, because water molecules are attracted to the glass, to the side of the glass. And so these water molecules are attached over here, and then other water molecules are attached over here. And then, of course, they hold on to the rest of the water that's in the middle, but they're too heavy, and so they hang out down here at this regular water level. Adhesion is also responsible for the evil pour. So when you go to pour something out of a glass, if you're really hesitant and you don't give it enough force, what'll happen is that water is going to trickle right down along the side of the glass, and then you're going to get that horrible thing. There's two ways that you can combat the evil pour. One is that you have to commit to the pour. So you can't be like, I'm going to pour. You have to be like, bah, I'm pouring. The other thing you can do is you can take another object that the water is going to be attracted to. If we're in the lab, we use a glass stirring rod, but sometimes at home I'll use a spoon. And you just put that glass stirring rod down into the center of the beaker, and then you pour your liquid down the glass stirring rod, and then the water is attracted to the glass stirring rod, and it will go down the glass stirring rod instead of coming back up against your beaker. Cool! Life skills in biology. This is a really cool picture that kind of shows you a combination of cohesion and adhesion. And so the cohesion is holding those droplets together. So we have these great bulbs of water, but then adhesion is holding that water onto that, I don't know, stem, leaf, pine needle, whatever that is that's sticking out there. So adhesion is holding really, really strong, holding that droplet there, but cohesion is holding water molecules together. So again, one more depiction, a cute little cartoon to show you what adhesion and cohesion are. Cohesion is water holding onto water. Adhesion is water holding onto some other polar or charged substance, some other polar or charged object. Capillary action is another really cool magical quality, and it comes about because of cohesion and adhesion working together. So cohesion and adhesion work together to move water up a really narrow tube, and we call those tubes capillaries. That's so cool. Okay, so if we had a wide tube, this would be like the meniscus in our graduated cylinder. These atoms are attached just by adhesion to the sides of the glass, but then there's so much water in the middle that they can't really lift each other up. The forces aren't that strong. But in this narrow tube, if we're only talking about individual molecules here, or just a few molecules, then these guys can grab and pull up, and then they pull up the next guy. And these guys grab and pull up, and they pull up the next guy. Grab and pull up the next guy. And so you can get capillary action pulling liquid up. You probably at some point when you were a kid did an experiment like this, where you maybe used celery and you put it in colored water, and you can get that colored water to pull up through the plant so that you can see that colored water going in there, and you have these beautiful things. This kid did a science fair type thing or an experiment kind of thing where he took a carnation and he actually split the bottom of the stem, and then put half of the stem in red and half of the stem in blue water. And when that water moved up, you got the red side and the blue side, but then you had some capillaries that sort of overlapped in terms of what they colored in the flower, and so you get some cool purple in there too. So it's kind of a fun experiment to do. I don't know, no matter how old I get, I still think it's really cool. But capillary action is the reason that we can have redwood trees that are hundreds of feet tall, because those capillaries, those teeny tiny little tubes, are able to pull water all the way up to the top of the tree so that those leaves can get water. And it's all just because of the polarity and the hydrogen bonding of the water. Surface tension, super cool when you see it happen. Surface tension happens because all of those molecules are pulling equally on each other. So you've just got this consistent pull. Everybody's pulling equally on each other. It's not one pulling one way or one pulling the other way. They pull equally on each other. And so what you end up with is this lattice or this framework of water molecules that form something that behaves almost like a solid if you've got a light thing that can distribute its weight. And so these water bugs are able to not break through the hydrogen bonds because those hydrogen bonds are so strong, and these bugs have evolved to distribute their weight across the top. And so surface tension allows water to act almost like it has a hard surface instead of a liquid surface that you can break through. All right, water, interestingly, has a lower density in solid form. Most of the time, what you have is when you have a substance and it goes from a liquid to solid, the whole definition of a solid is that the molecules are closer together and they're arranged in a uniform manner. That's what a solid is. A solid is molecules closer together arranged in a uniform manner. But in water, the hydrogen bonds make it so that the molecules stay spaced farther apart. So when water freezes, it actually makes these loose crystals, and then those crystals are less dense than the liquid water. And that makes it so that solid water actually, solid water actually floats on liquid water. If you take any other substance and put it in solid form, and take that solid and put it inside the liquid form, the solid form is going to sink down to the bottom. It's not going to float. But water is unique because of the hydrogen bonds. Water also has a higher specific heat. What that means is it takes a long time to heat up, and it holds its temperature longer once you stop applying the heat. Okay, so water takes a long time to heat up, holds its temperature longer when the heat is no longer applied. So living in Chicago, you've probably seen on the news where they talk about the weather and they say cooler near the lake. Well, why is it cooler near the lake? Well, if it's summertime, the lake has gotten really cold and frozen in the winter, and it's trying to warm up, but the lake is really, really cool. It's taking a long time for the lake to heat up. And so the lake is staying really cool, and so you get these lake breezes that come off the cold, this air that blows off the cold lake, and it blows that colder air over to us, and so we feel nice and cool when we're near the lake. But the opposite is also true. In the wintertime, it's gonna be warmer near the lake. In the winter, it's warm near the lake because the lake has heated up all summer long. It's finally gotten warm and it holds on to that warmth. And so breezes will come off the lake and we'll get that lake effect where it's a little bit warmer down near the lake. And so that lake just acts as sort of this reservoir for heat and holds on to it for us. Water will also repel nonpolar substances. Since it's polar, it wants to be by other polar things but does not want to be by nonpolar things. The most common nonpolar thing that we talk about, those would be fats, like fats and oils, lipids, things like that. Water is also really good at dissolving polar substances. So things that have polar covalent bonds in them, or even ionic bonds, water is really good at dissolving those. But wait, oh my God, what do you mean when you dissolve something? Okay, we're getting ahead of ourselves. Let's get on to that. So we have a mixture. A mixture is a combination of two or more substances that do not chemically react with each other. So we're not going to get a chemical reaction. So in a mixture, there's no chemical reaction taking place. There are three kinds of mixtures. There are suspensions, which I'm going to talk to you more about. There are colloids. You don't need to know about colloids, just know that they exist. And there are solutions. You do need to know about solutions, and I'm going to talk to you about solutions. In a suspension, the particles are large and they're unevenly distributed. You can usually see the particles of a suspension with your naked eye. So something like, oh no, I lost a caption here, like dust and pollution in the air, the various things that are in soil, sand that's in water, those are all suspensions. Salad is a suspension. So you've got actually big pieces all mixed together and you can see them. In a solution, you have particles that are really, really tiny and they're evenly distributed, okay? So you have this, what we call homogeneous distribution. So you've got an even distribution of teeny tiny little particles. In a solution, one of the substances is dissolved in the other substance. The definition of dissolved is that a substance has been dissolved when it has been broken down to the molecular or the atomic level and no longer has properties of its own. So when sugar stops behaving like sugar or looking like sugar, when salt stops behaving like salt or looking like salt, when it seems like it is this whole other thing or it seems like it completely disappears, then we know that that has dissolved. A solution consists of two parts. It consists of the solute, which is the substance that's getting dissolved, and the solvent, which is the substance that's doing the dissolving. So here's an example of the solute is our blue granular material. The solvent is water in this case. And when you mix the solute and the solvent, you get a solution. So you can see that you no longer have these blue granules. You no longer have plain old water. You have now this whole, this different thing, but no chemical reaction took place. All that happened was our solute broke down into teeny tiny little itty bitty pieces down to either individual molecules or separated atoms. Okay, so it says, I just love hanging out with you, chloride. Sodium. Oh no, is that water? What? Where? I'll never forget you. So the reason water can work to dissolve things, so this would be an ionic bond that we have here, is that water comes and it basically posses up. It comes in and there are so many water molecules that they then, with their hydrogen bonds and their oxygens that are really good at pulling at electrons, are able to go and just kind of surround these ions and grab them and pull them apart. And so then these ionic bonds can get disrupted and you have these two then molecules or atoms that get pulled apart from each other. So we can disrupt the ionic bond between the sodium and the chlorine and we end up with this dissolved salt that is now separate. And we've got two different things. Now in the case of something like sugar, C6H12O6, we don't actually pull the C's and the H's and the O's apart from each other. We just pull one sugar molecule from another sugar molecule and then they get broken down so that it's one sugar molecule surrounded by water, another sugar molecule surrounded by water. So we go down to the molecular level in that case. All right, we're almost done. Okay, so speaking of ions, water is capable of breaking apart into ions. It can break apart into a hydrogen ion, which you'll also hear people call a hydronium ion. So you can have a hydrogen ion or a hydronium ion, which is H+, and a hydroxide ion, which is OH-. So you have water here, H2O, that can break apart to be a hydroxide or hydroxyl ion, and the hydronium ion or the hydrogen ion, okay? Now, they're showing this hydrogen pulling off, but just as easily, this hydrogen could pull off, okay? It could be either one. If a solution has an equal concentration of hydrogen ions and hydroxide ions, then what we say is that it's neutral, okay? So these brackets mean concentration, okay? So if our concentration of hydrogen ions is equal to our concentration of hydroxide ions, then what we have is a neutral solution. It's balanced, okay? On the pH scale, that substance is going to have a pH of 7. So 7 has been decided. That's the middle. That's neutral. That's where we are. So hydrogen and hydroxide are even. Awesome sauce. Okay? Acids are substances that, when you add them to water, are going to end up giving the overall solution more hydrogen ions than hydroxide ions. Okay? So now our concentration of hydrogen ions is greater than our concentration of hydroxide ions. So we have way more hydrogen ions than we have hydroxide ions. On the pH scale, these substances are going to have a pH of less than 7. So we're going to go from 7 down to 0 on the pH scale. And the closer we get to 0, the stronger of an acid we have. The opposite is true then for bases. Bases are substances that when you add them to water are going to end up giving the overall solution more hydroxide ions than hydrogen ions. So our concentration of hydrogen ions is going to be less than our concentration of hydroxide ions. On the pH scale, those substances are going to have a pH of more than 7. So we're going to go toward 14 on the pH scale. Again, the closer we get to 14, the stronger our base is. So we have neutral at the middle, and then it's a spectrum that goes out so that we've got neutral, weak acids and bases, medium acids and bases, strong acids and bases. Each number on the pH scale represents a factor of 10. In other words, if a substance has a pH of 6, then it is 10 times as acidic as a substance with a pH of 7. Okay? So if we go one step on the pH scale from 7 to 6, then we're going 10 times as acidic. Okay? So take a second, pause this after I finish reading the question, figure out for yourself, how much more acidic is a substance with a pH of 3 compared to another substance with a pH of 6? Hit pause and work that out. Okay, hopefully you worked it out. So if we go from 6 to 5, that's a factor of 10. From 5 to 4 is another factor of 10. And from 4 to 3 is another factor of 10. What that means is that we have 10 times 10 times 10. So we end up with 10 times 10 is 100, times 10 is 1,000. We end up with 1,000. That means a pH of 3, that substance is 1,000 times as acidic as something with a pH of 6. 1,000 times as acidic for those 3 steps. So I have another problem for you. How much more basic is a substance with a pH of 11 compared to pure water? So there's 2 issues here. You have to figure out what the pH of pure water is, but then you also have to figure out that comparison. Go ahead. I'll wait. Hit pause so I don't have to wait so long. Okay, so if we go from 7 to 8, that's a factor of 10. 8 to 9 is a factor of 10. 9 to 10 is a factor of 10. And 10 to 11 is a factor of 10. So we had 4 jumps. So we need to do 10 times 10 times 10 times 10. That's going to give us 10,000. So something with a pH of 11 is 10,000 times as basic as pure water. That is a lot of basic. Finally, a buffer. A buffer is a substance that's going to pull ions out of a solution to prevent fast, drastic changes in pH. Because the last thing we want to do is in something like our body, put an acid in and have the whole pH of our body go all caterwonky. So buffers help us maintain, remember, homeostasis. They help us maintain what's going on inside our bodies without having pH changes all over the place. You've seen buffers advertised before. A lot of medicines will say on them that they're buffered. Vitamin C, specifically the chemical formula of vitamin C is that vitamin C is an acid. Okay, and so if you're going to take a vitamin C pill, you want to have a buffered vitamin C pill so that when the vitamin C goes into your body, you get all of the benefits of what the vitamin C molecule does, but you don't completely destroy what's going on in your stomach, which could then give you heartburn and make you feel really terrible. There are actually companies that make use of science words in their products. So bufferin. Bufferin has the word buffer right in it. And that's because aspirin, another really common acid that many of us put into our bodies, aspirin gives people heartburn when they take it. But if you get a buffered aspirin, then when you put the aspirin into your body, again, it doesn't throw your stomach out of whack and it doesn't give you heartburn and make you feel badly. So a buffer is really good for neutralizing and keeping those pH changes from being really fast and drastic. It controls that and keeps you from having these spikes of an acid or a base in solution. So buffers, by the way, will work on acids, but they will also work on bases. And there you go, all of the magical, phenomenal properties of water.